Hi, my name's G. My call sign's G4LA, and I've not been desperately well recently, so I had to find things to do. While I was digging around in my semiconductor boxes, I found something called a switch capacitor audio filter, which I'd never used. It's just a chip, but in order to use it, I needed a rather special kind of audio signal generator, which has something called a sweep function. And in all the junk that I possess, I don't actually own one, so I thought I'd better make one. So scanning around the place, I realised I had an Arduino, which is an Atmel based computer. That's the little blue thing that you can just see down there. And I decided to implement a digital to analog converter over the top of it, so that I could get the sweep function I wanted and a lot more besides. And it's been great fun, and I've thoroughly enjoyed doing it. So let's go and have a look at it, shall we? Oh, and before I forget, thanks to Caroline for letting me borrow her video camera, because my webcam's useless. Anyway, bear with me. Right, first things first. First of all, this is what it all looks like. If we look over here, we've got the Arduino, 2 data ports. I need to be able to tell the Arduino what I want it to do, or how I want it to behave. So there's 3 buttons that can talk to the Arduino. One's mode, which says the type of waveform I'd like it to produce. Then there's down, which means go down in frequency. Up means go up in frequency, and sweep, which is the thing that I'm really looking for, which starts at a very low frequency and then goes up to a high frequency so that I can sweep the filter. Now, to convert numbers, which is what computers are really good at, to an audio signal, you need to go through a network of some description, and I'm using an R-2R network, which I'll explain in a little bit. And then the output of that goes to a buffer amplifier, which just isolates the R-2R network from the outside world. So I'll explain that a bit more about that right now. Here we go. The next bit is a bit techie. So for those of you who are technically minded, go and make a cup of tea or something. Or a glass of wine. Yeah, go and have a glass of wine or something. Yeah, here we go. This is what an R2R network looks like. Mine is an 8-bit R2R, which means I can have 256 levels of output, which isn't bad for the kind of thing I want to do. The digital to analog converters that you have in your CD players are very often 16-bit, and a very posh one will be 32-bit. But they don't always do it this kind of way. R in this case is 10k or 10,000 ohms, and 2R is 20k, which is 20,000 ohms. And if you look at the top there, all along there, that's the inputs into the R2R array, and the output is way over here, over there, and that goes off to the buffer amplifier. Now, I'm not going to explain all the ins and outs of how an R2R network works. If you go on YouTube, W2AEW, and I can't remember your name, sorry, but you've done, or he has done, a really brilliant explanation as to how the R2R network works. So let's go through it and see how I've implemented it on the Arduino. And here it is. Now, what I'm going to do is I'll just scan around it a little bit. But what I'm going to do is I'm going to set the camera up in a minute so that I've got my hands free, and then we'll do some experimenting with it. But that's it. Be back in a minute. Okay, and I'm back again. Right, well, I've got the camera all set up so that I can use my fingers. Okay, obviously the thing to the left of the Arduino is not anything to do with the project really. As it happens, that is an origami F15, and it took me longer to make that and dozens of attempts than it did for me to make the Arduino. But anyway, it's quite pretty, so guess what you guys are getting for Christmas. Okay, let's get into this thing, shall we? Right, first things first. On this side here, that's port D, and that's port B, and this area here contains the R-2R network. If you do decide to have a go at one of these, it's quite important that the resistors are pretty closely matched. A good way of trying to establish that is if you get a bandolier of resistors, those are all 10Ks, and to make the two Rs, I've just put two resistors in series. If you get a bandolier of resistors, because they're all manufactured at the same time, you usually find that they're very, very close. You need to be better than 1%. And I measured each and every one of them. There were a few that were a bit outside, so I threw those away. Well, I didn't. They just went into my junk box so I could use them for something else. But that got that lot made up. Here's the input buttons. That one sets the mode or the type of waveform I'd like. That button there initiates the sweep. That button there makes the Arduino tell the DAC to go up in frequency, and the bottom one tells the Arduino to go down in frequency. If we look towards the back, there's a little buffer amplifier. It's only an op-amp, and it's a unity gain op-amp. The output of the DAC needs to see a really high impedance. It can't talk directly to the outside world, so I use a buffer amplifier just to be able to do that. Let's have a look at it in a bit more depth. There we go. There's a few supporting components, not very many, but I have put in quite a lot of decoupling, which is quite important. Because we don't want lots of noise getting into the op-amp, because it would rather defeat the object really. So that's pretty much all it is. It took me a couple of hours to make. In fact, it took me more time to go down through a bandolier of about 1,000 resistors than it took me to actually build the rest of it. A little trick here. You've probably noticed that it's quite expensive buying sockets on a 0.1 inch pitch. Another way of doing it is that is 1/2 of an IC carrier, just cut in half, and then this bit, the switch module, just plugs in quite nicely, just like that. It's not ideal, but and the reason I did it, apart from anything else, was I couldn't find any 0.1 inch sockets, so I kind of had to do it really. So that's a quick tour of what how the device is implemented. What I'll do now is I'll wire it up and connect it to some test equipment so that we can see and hear, I hope, what's going on. And back again, or I would be. I'm just trying to get this tripod to be a tripod. Hang on, bear with me, folks. Right, I've hooked up the Arduino and the digital to analog converter to a frequency counter and an oscilloscope. The unit, or the board to the right, is an audio amplifier, very simple one, and I made it a couple of years ago. It's a Class A amplifier, because for this kind of work you really want to avoid any additional distortion being introduced by a Class B amplifier or a Class AB. For the home brewers amongst you, especially the QRP guys, you're probably wondering why I didn't just use an LM380. The LM380 is wonderful, but you don't have much control of its insides. The design there is straight out of solid state design for the radio amateur, and if I had my way, I'd make it compulsory that all radio amateurs had a copy of it. It's a fantastic book, and I thoroughly recommend it. Anyway, that's going to sit there, and so that we can hear the output. I've actually turned it right down for the minute, because the noises can be a bit distracting while we have a look at the waveforms that the Arduino and the DAC can make. But I promise we'll listen to some noises later. Anyway, let's go and look at the test equipment. Bear with me. And I thought I'd tidied my bench. Okay, on the in the right hand side, we've got my old and trusted Dana frequency counter. Gosh, I've had that a long time, and still working beautifully. Still, I calibrated it a couple of weeks ago, and it's still bang on. How did I calibrate it? I calibrated it against WV, which transmits on 10 megahertz. Dead easy to do if you know what you're doing. I'm sure you don't want to see my finger. Right, on the other side, we have my trusty, let me try and get this about right, 453 oscilloscope, late 1980s, no, late 1970s I think, and shortly to be replaced, but it does the job. So what we'll do is we'll have a look at the waveforms that the Arduino and the DAC can make. So let's have a go. Now there's bound to be a bit of strange camera angles and all the rest of it while I lean over and press buttons, but I'll do my best not to disturb things too much. But bear with me. It's the first time I've done anything like this, so haven't quite got the hang of it yet. So there we go. Our first waveform is a square wave, as you can see. And it's not too bad. There's a tiny bit of sag, but I suspect that may be because I haven't compensated the scope lead properly, properly. So that might explain that bit of sag. But yes, it's a pretty good. It's a pretty good square wave. Okay, let's make something else, shall we? Right, a leading edge ramp. Now, a lot of people are more familiar with with its very close cousin, which we'll see in a minute. I know a use for leading edge ramps, but I better not say too much. But it's pretty easy to generate one, and there we go. Pretty precise. The nice thing, although I haven't done it for this demonstration, is if I wanted to, if you look at the very peak of that, there's a very sharp angle as it starts coming back down the ramp. Using the Arduino, I could roll that off, because that very sharp transition is almost bound to be spraying RF all over the place. But yeah, by rolling it off, a little bit, it would be possible to reduce any interference. But yeah, it's quite nice, isn't it? Okay, let's do the next one. Right, this ramp is a so-called trailing edge ramp. I can think of another. I can think of uses for those as well. For electronics guys, you're probably more familiar with seeing a ramp going this way, because it's used. Well, it certainly was used in televisions for generating sweep, but you've probably used it in voltage-controlled oscillators for creating sweep. Using a varicap diode. Again, there's a bit of bounce down at the bottom, but again, it would be pretty easy to do something with the top end of that spike, just to make it roll out a bit better. Let's put it that way. Okay, on to the next one. The good old sawtooth. That's come out pretty nicely. Again, I can't remember the last time I used a sawtooth. I must have done, but anyway, it's there, and far easier to implement with a few resistors that cost pennies than half a dozen semiconductors. For charging a capacitor, hitting the peak, discharging it slowly. Working out when you've got to the bottom and when to start charging again. It's so much easier to do with a computer and a DAC. Okay, on for the next one, eh? And we have a sine wave, ish. Now, if you look carefully on the rising edge, there is a little bit of jitter, and that's because the way that I generate the sine wave is the Arduino, powerful little computer that it is, you can't actually use the sine function, well you could, in real time as it were, because the sine function is pretty slow. So what I've got is a lookup table. I use the sine function to create a lookup table, and then for every step that I take the value from that table. Unfortunately, because I've only got 256 discrete voltages I can use, it does fall to bits a little bit, because it's not possible to get the absolute accuracy that you'd get with, say, a 16-bit or a 32-bit DAC. But for 8 bits, I don't think that's too bad. Okay, let's go on to the next one. Now I can imagine you thinking, what the hell's he done there? What's gone wrong? Well, let's slow it down. Now that is a random output. What's happening there is I'm using a randomizing function to create noise. And what it actually sounds like is noise in a thunderstorm. And the reason that I have implemented this is to see how the filter copes with really weird and wonderful transitions. It's usually fairly easy to predict what's happening if you've got a fairly clean waveform coming into any kind of filter, but in real life, coming off this beast, there's usually lots and lots of noise and crackles and bangs. And that's one of the things that which we're trying to get rid of. But some filters don't handle it at all well. They don't like the rapid transitions. So there you go. Pretty, isn't it? I bet it works out that appeals to some of my more artistic friends than perhaps some of our engineers. Strange, isn't it? We spend most of our lives trying to avoid noise, and then I go around trying to make it on purpose. Okay, for the next one. Now the next one's really fun. If you've got a computer and a DAC, you can make any waveform you like this. Oh, not quite. Right, how weird is that? That is a made-up waveform I just told the or just programmed the Arduino to create a waveform like that. So again, a huge advantage. If you wanted to achieve that in using discrete components, it would take you ages, ages and ages and ages. But doing it with a computer makes life so much more straightforward. So there's some demonstrations as to the kind of waveforms you can make. Let's go back to the beginning. Bear with me. Because the other thing that we're going to want to do, if it's going to do it, no, I don't think it is. Maybe not. Hold on. What I want to do is see if, oh, maybe it's fallen off. Well, we can see it just as easily here. What I'm doing here is I'm just increasing on this square wave. You can see I'm increasing the frequency of the square wave, and it will go up to about 10 kilohertz, which kind of surprised me. But and then we can go the other way. Hold on, I'm sorry. We can go down. There we go. Now you can't tune it in the same way that you might in a movable bed vibrator, because the device can't sort of do two things at the same time. It can't turn out a waveform and adjust the frequency at the same time. Nice to do that, but at the minute I can't do that. And then the last one. What have we got going on here? Now watch that waveform. Can you see it's beginning to scrunch up? That means it's going up and up and up and up and up in frequency. This is the frequency sweep function I wanted, and as you can see, it was pretty easy to do in with the Arduino, and that is all being generated by numbers and some counters in a loop. Right, there we go. So that's what the waveforms look like. So let's have a listen to them, shall we? Welcome back to this side of the bench. I'll turn up the noise a bit. Okay, there we go. That's the square wave. I'll just switch it off a minute and we'll pitch back on again. And we'll go up in frequency or down. Square waves are really horrible. As you can, I'm not sure that this little camera will pick up that noise, but there we are. Let's have a listen to a leading edge. Okay, there we go with the leading edge. And again, we can go down in frequency, and we can go up in frequency if I'm patient. Okay. So let's have a listen to a sawtooth. Okay, I think we've just missed the sawtooth, the first one. That's a sine wave. Just bring it down in frequency a bit. If I was to change anything, I'd find another way of doing this, but it'll do for what I want to do. Let's go on to the next one. Right, that's the noise. And if you've ever listened to a radio on single sideband, that sounds like a really bad thunderstorm or static rain. Not a very pleasant sound, but it's there nonetheless. And what about the weird waveform? Right, okay, that's that weird waveform. And the ultimate. Here's a sweep. There you go, and that's what I aimed to achieve, and with the help of the Arduino, a R-2R network, a buffer amplifier, and I don't think that'll come out. There's the program. Oh no, we're not allowed to call them programs because it's an Arduino. We have to call them sketch. And if you'd like to have a go at making one of these yourselves, then just send me an email. I haven't drafted the circuit diagrams yet, but if you want to have a go, I'll draft up the circuit diagrams in Design Spark, and I'll ship the source code over to you. Anyway, I hope you've enjoyed it. I certainly have had great fun, and well, I'm trying to work out what to do next. I guess I'm going to have to get my switch capacitor mode filter out. Oh look, there it is. But I need to do some changes to it. Okay, so that's all from me. 73 and 88 to the ladies, and look forward to the next one.